Now, on lesson one, we introduced the concept of our IDMT relays, and in lesson two, we really went into some calculations and a few examples on getting what we call our IR. And now, in this lesson, we are going to look at our time setting multiplier, and we are going to also look a little bit into the grading. Then on the last lesson of this module, we are actually now going to start doing some calculations onto our radial systems. So therefore, what I want us to just look at is the type of IDMT relays that we have. If you look at the bottom of the slide, where we have what we call our standard inverse, our very inverse, our extremely inverse, and we've got our definite time. If you look over in this slide, it will show us what the formulas are for each of those relays that we talked about. So the first one being our standard inverse, which is TMS multiplied by 0.14 divided by our IR, which is into 0.02 minus 1. Our very inverse being TMS times 13.5 over IR minus 1, and our extremely inverse being our TMS times 80 over IR squared minus 1. Then our long time standard earth fault, which was our definite time, would then be equal to TMS times 120 over IR minus 1. So again, our IR, remember, it is that I over our IS, and then where I was our measured current that we have on our system, our IS was our relay setting current. And then our TMS that we are now talking about is our time multiplier setting, which is the one that determines the travel that the disk is going to have. So in here, you're given a system where you've got a CT, you've got a nominal current on our relay, and you've got a plug setting of 90%. And we're asked to calculate what our TMS is for the system, which needs to trip in 0.6 seconds and a fault current of 12,500. So we start up by calculating our I secondary like we did in the last examples that we did, and then we calculate our IR. If you are like me and you don't like doing too many calculations, you can always go straight to our IR calculation. And how would you do it? It would be that fault current that you have on the system. Then you would divide by the multiplication of your 750 times your plug setting. Okay, why are the fives not being put in? Because my fives will then cancel out. Okay, the 5 that was in my I secondary on top and the 5 that I have now in my formula on IR would then be cancelled out, and I would get exactly the same answer. So please try it again, guys. It would be your IR is equal to your IP or your I fault divided by your primary current on your CT multiplied by your plug setting, and see if you're getting this 18.52. If you know you're going to forget it, you can always go the long way. I secondary first, and then you go and calculate IR afterwards. Then after that, you can then go to a formula for our standard relay, all right? And you can then say it's going to be TMS is equal to 0.14 over your IR is to the 0.012 minus 1. And that can be able to help you to calculate your TMS value. How do I know that I've utilized the right formula? Because they said my relay was a standard inverse IDMT relay. So if they had said it was a very inverse, I would utilize the other formula, and extremely the other one. So you must know what type of relay that they're saying you must use for you to be able to calculate your TMS properly. Otherwise, you won't get the right answer. Then in example 6, I like it because now they've changed and you can see that I'm no longer using my standard, but I'm using my very inverse IDMT relay, all right? And then I've even gone and put in there so that you can remember that its formula is going to be T is equal to TMS multiplied by 13.5 over your IR minus 1. So you've got a CT, you've got a fault current, and then you've got a relay nominal current. Then you've got your trip time, which is 0.4 seconds, and you've got TMS, that is 0.3. So in this case, now they're saying calculate the plug setting instead. So you're working the other way around. So what you do first, you can still go and calculate what your A secondary is, and then you get an answer there at the bottom. Then you go to your formula for your T, okay? Because in that formula for your T, you're going to have that IR scenario. That is what you're going to be looking for. And then I found my IR over here to be equal to this 9.125. I then go and take that IR and I put its formula so that I can be able to calculate my plug setting. And there I got a plug setting of 182%. Always remember, you asked to calculate a plug setting. In these scenarios, the plug setting must always be between the values of 50 and 200%. Then we're going to talk about time grading, right? Margin. So our time grading, as we defined before, we said it was the time interval that must be allowed between the operation of your two adjacent relays. Okay, so if you had a feeder D and an E, it is that time difference between those two relays. Then if a grading margin is not provided or it's insufficient, then it means that you're going to have more than one relay operate for the same fault. This will lead to difficulties for you as an engineer and for the guys that need to go and fix or find the fault to be able to determine exactly where that fault was at. So unnecessary loss of supply to some of the consumers will happen, and a lot of wastage of time to be able to work out where the fault is will also be done in this case. So our time grading depends upon the following elements for us to be able to determine it correctly. Your fault current interrupting time of your circuit breaker. Okay, so it's the interrupting time of your circuit breaker, the time that it takes to actually trip after you've sent the signal to it. Then you've got your relay errors. Then you've got overshoot time of your relay, and you've got the CT errors, and you've got your final margin on completion of your operation. If you are not given a time grading, okay, looking at just these points that we've just defined now, we usually assume a value of 0.4 seconds then to be our time grading, because it will take care of these as a minimum. So that's what you utilize. If you're obviously given a value, that's what you would use. So your grading margin is the discrimination then between these relays in the power system and then all the things that I've just defined above, all right? You've got 4 of those factors that are going to actually be given time that comes to that 0.4 seconds I was talking about. So it's your variation from the ideal characteristic curve of 0.1 seconds. Your overshoot of your disk is 0.05. Your circuit breaker operation at 0.15, and then you've got your contact gap. Ensure that the relay has your short distance to travel when it's cleared for discrimination at 0.1 seconds. And that's how you come to that 0.4 seconds. So this is the minimum discrimination between your relay operations at your maximum fault level. All lower levels of your current time interval should be greater. And if obviously we are not at our maximum fault level, then you can expect that time grading to also be less. So your relay time grading margin is the relay errors and overshoot depend on the relay technology that has been utilized. So an electromechanical relay, which was our first of these, has a larger overshoot time than your numerical relays. So your normal grading margin was 0.4%, which while under the best conditions, even lower intervals may be practical. Okay, so that's why they can give you ones that are 0.35 is famous and maybe sometimes 0.3. Then we are just going to now highlight and say system with impedance between your bus bars and how we go about doing our calculations. So if we have the system to be protected that has equipment with substantial impedance values between your bus bars, it will cause a change in your fault current at the different bus bars. The calculation to trip the times of your protection relay so that the proper discrimination is achieved has got the following procedures that you must follow. You start with the relay furthest from the source and calculate the minimum plug setting, which is your PS, using the available full load data information that you have. Then you have got your trip time of the relay and you calculate the TMS of that relay using the fault current. Then you use that available full load data and calculate your second plug setting, and then you would go. After that, you calculate the trip time of the relay by using the fault current on your immediate remote side of the relay. Once you've done that, you calculate the trip time needed for the second relay by adding the discrimination time to the trip time of the first relay. And then your TMS calculation gets done. This will ensure that your relay 1 and relay 2 discrimination at maximum fault current furthest from the bus bar. These will become clear, I think, without me having to read them when we start doing the example in your next lesson. So I'll leave it here. Go and study them so that when we do them, the more you practice, you can be able to go back and look at how you do these. So in this slide, it shows us that you can actually put in information for your relay data, or you're taking in your fault current, what is your maximum and your minimum in your system. You're taking in your maximum load current, your CT ratios that you have, and your relay current settings, which is